Recently, I was shown this paper. Alright, I'll give it a moment. And I gotta say, it piqued my interest. I knew almost right away that I had a video on my hands. Now, to give a quick spoiler, it pertains to the spin of galaxies in our universe. So for today, we will cover why things spin, why this is relevant in space, some facts about our Milky Way galaxy and its spin direction. Then we will get into the study, what it found, and some possible explanations for why that might be. So strap in, grab a drink, and let's get into the video. Let's start with the question, what is angular momentum? In short, it is how we measure the rotational motion contained in an object that is rotating or revolving around a point or an axis. So let's break this down a bit more, starting with its equation, which I will have up on the screen. L is the angular momentum, and it is equal to I, the moment of inertia, and W, the angular velocity. But what do these two variables really mean? The moment of inertia describes the object's rotational mass. It tells us how the mass is distributed relative to the axis of rotation. The angular velocity describes how fast the object is rotating around its axis. So basically, angular momentum is a product of these two values. I would also like to note that angular momentum is a vector quantity. We won't really be getting into this further, but what this means is it has both direction and magnitude. We can use the right-hand rule to visualize direction. If you point your fingers in the direction of rotation, which for me would be like this, your thumb will provide the direction of the angular momentum vector in a 3D space. Now you might be saying at this point, man on the internet, what is an example of all of this? And I am here to tell you that it is likely you have seen this in action before. Picture a figure skater performing a spin. Her arms will start outstretched, and she will already be spinning quickly. But the moment she brings her arms inwards, she begins to spin faster. Then, if she stretches them back out again, she slows back down. This is angular momentum in action, but it also demonstrates to us what is known as the law of conservation of angular momentum, which states, a rigid spinning object will continue to spin at a constant rate and with a fixed orientation unless influenced by an external application of torque. If you've heard the term closed system before, what it means is that it is unaffected by outside sources, such as the torque we just mentioned. So, if we go back to our figure skater example, the reason her spin rate changes depending on her arms is because her moment of inertia is changing, but her angular momentum is conserved. Now here on Earth, we are not in a closed system. An ice skater will eventually slow down due to friction, which can be viewed as a form of torque, and a spinning top can be viewed in a similar fashion. As friction slows it down, it will experience precession or wobble, eventually losing its angular momentum. But what about in space, where objects are much closer to being in a closed system? All things in space spin, from as little as asteroids to as large as galaxies, and honestly, even beyond that. Unlike here on Earth, though, most of these objects are much closer to being in a closed system, so they retain their spin for much, much longer. Let's take Earth for example. We know it takes about 24 hours for it to make one full rotation. At the equator, this comes out to around 1,038 miles per hour, though that speed varies depending on where you are on the planet. So, it is spinning rather quickly. And while this speed has been affected slightly by things like tidal forces with the moon, it has been spinning like this ever since its formation 4.5 billion years ago. So as we can see, its angular momentum has surely been conserved. Now let us step up to the Milky Way galaxy and even others like it. Our whole galaxy does in fact rotate. Like Earth, its speed varies depending on how far out from its center you are. Found at the center, and what everything is orbiting around, is a supermassive black hole called Sagittarius A star. This behemoth is around 4.3 million times the mass of our sun. So it's a heavy boy. Our solar system, which is around 27,000 light years away from the center, takes about 225 to 250 million years to make one orbit. There are between 100 and 400 billion stars in the Milky Way, and they are all orbiting the center, that black hole, just like we are. Like with all things that spin, the Milky Way also has a direction. When viewed from the top of its galactic plane, it is spinning clockwise. While we can't actually view the Milky Way like this, we are still able to work out the direction that it's going. This also means that the perceived spin of a galaxy does depend on our viewing angle of it, right? So if the Milky Way was viewed by an observer below its galactic plane, it would be spinning counterclockwise to them. While I wanted to draw attention to this, it won't really come into play when we are going over the paper I mentioned at the start of the video, but it is still worth noting. So now we know that pretty much every galaxy rotates and that they will have a direction. Currently, scientists believe the universe to be isotropic. What this means is that it is roughly the same everywhere we look. So when we apply this to spin direction, we expect to see about a 50-50 split between clockwise spin and counterclockwise spin. And while this may very well be true, the study I mentioned earlier just might reveal a different story, and so let us get into that now. Before we get into what was studied here, I would like to draw attention to a couple of things. From what I could find, this is the only study that has been done in this area. Along with this, it was done on a relatively small sample set, so we want to take everything presented in it with a grain of salt. Normally, we would want more than one study done by different scientists or groups, and we would want the studies to be done on much larger sample sets. That aside though, I still want to talk about it as I do find it interesting. The study was done using data from the JWST Advanced Deep Extragalactic Survey, or JADES for short. A total of 263 galaxies were observed, and the main thing looked at was their spin direction. So now you might be curious, how do we know what direction these galaxies are spinning? So there is more than one way we can determine this. One of them is simply by looking at them, especially for spiral galaxies. For this, let's have a look at this image here. When we look at the arms of a spiral galaxy, it can pretty much give away its spin direction to us. For example, these are spinning clockwise, while these are spinning counterclockwise. Let's say we can't quite tell by looking at it though. Another way of determining galaxy spin direction is through the shifting of its light in what is known as redshift and blue shift. So redshift is what happens when the wavelength of light increases or is stretched on its way to our detector. This happens when the object or part of the object is moving away from us. Blue shift is kind of the opposite. It's what happens when the wavelength of light decreases or shrinks on its way to our detector. And this is what happens when the object or part of the object is moving towards us. So by putting these two together when observing a galaxy, we can pretty much figure out what direction it is spinning. Now, what exactly was found here that is so interesting? It is that we did not see that expected 50-50 split in the spin direction of galaxies. Rather, 2/3 of them are spinning clockwise, while the other 1/3 of them are spinning counterclockwise. So, let's go into some possible explanations for why that might be. Here, we are going to start with some more likely explanations and then move into a more exotic one at the end, beginning with sample bias. So like I mentioned earlier, this so far is the only study that has been done on this, and it was done on a very small sample size with only 263 galaxies. It is just not feasible to really judge something as overwhelmingly large as our universe on something as tiny as this. We might just be looking at a particular section of galaxies that happen to display this uneven distribution of spin direction, and for all we know, if we expanded this out to 500 or 600 galaxies or more, the results could change. Or if we sampled different areas of the sky with thousands of galaxies, then we might end up seeing closer to what we expect. Next, we have quasars and the cosmic web. You may have heard of quasars before. They are galaxies that have very active supermassive black holes at their centers. By active, we mean they are feeding on material around them. So they are surrounded by spinning disks of very hot material. A lot of times, we can even see this material getting spewed out in jets along their axis of rotation, which helps make them a lot easier to study. Quasars can shine so brightly that they outshine all the stars in the rest of their galaxy combined. So what might these quasars tell us about the spin of other galaxies? Let's have a look at this study. One of the things noticed in it is that rather than being evenly distributed, all of these quasars have seemed to form in a large-scale cosmic structure known as a filament, or a cosmic web, if you will. And by large, I mean huge, spread out by billions of light years. Another thing that was noticed in the study is that the rotation axis of some of these quasars were aligned with each other, meaning they were rotating in the same direction. And not just like each other, it was found that they were linked with the structure of the universe on large scales as well, at least at the time. So let's say more galaxies are linked to this filament, even if they are not quasars. The influence of them and how they formed could help explain why we saw the uneven split in the more recent study. Our results also might just be skewed by our movement here on Earth, our solar system, and even our galaxy itself. On Earth, the redshift and blueshift measurements from our telescopes can sometimes be skewed by our movement, depending on where they are looking. Now, this data came from JWST, which is orbiting the Sun with us, and it is at the L2 Lagrange point, and this could add extra motion as well. Even going beyond this is the movement of our solar system through the Milky Way. We are flying at around 500,000 miles per hour as we rotate the Milky Way. All this to say, we could be seeing a bit of bias in the redshift and the blueshift, changing the representation we see in the rotation of distant galaxies. So this last one, while a cool sounding idea, is the least likely to me, but I still wanted to include it here. Us living in a black hole stems from the thought or idea that every black hole out there ends up creating its own universe from the matter it collects, rather than creating a singularity. Part of what gives this credence is that there is no difference between the horizon, like the visible horizon of our universe, and the event horizon of a black hole. Both are a cutoff point from which no light or information can ever reach us. Because all black holes rotate, all the matter within the black hole would likely have a preferential spin, and this could explain why so many of the galaxies we saw spin clockwise, and even why the universe itself seems to spin clockwise. So this turned out to be one of the most fun, but also kind of one of the hardest videos I've made. And while we don't have enough data yet to really draw any conclusions, I am curious to see if this is studied more in the future. And with telescopes like JWST available to us, we certainly can. But I'm curious, did you enjoy this video? What do you think the most likely explanation is? Sound off in the comments below. I would love to hear it. Please also like and subscribe, because I really do appreciate it. With that, let us all step outside tonight and look towards the stars.